Let's go ahead and work on the improper integrals from the handout. If we look at number 3, it's the integral from -8 to 27 of 1 over x to the 2/3 dx. Why is this improper? Well, it's discontinuous somewhere in the bounds. Between -8 and 27, what's the number that causes a problem? It's discontinuous at x equals 0. This is an example of a type 2 improper integral, and the discontinuity occurs between the two bounds. So the way that we're going to solve it is to split it up into two integrals. We're going to start with the integral from -8 to 0 dx over x to the 2/3 plus the integral from 0 to 27 dx over x to the 2/3. And we're going to look at each one separately. Where's the discontinuity in the first integral? It's the upper bound. In the second integral, the discontinuity is the lower bound. So we're going to rewrite these as the limit of an integral. The first one is the limit as b goes to 0. It's going to have to approach from the left because it starts at -8. Integral of -8 to b dx over x to the 2/3 plus the limit as, let's use a different constant, c goes to 0 from the right, because we're coming from the right because our upper limit's 27. The integral of c to 27 dx over x to the 2/3. Okay, after finding the antiderivative, we get the limit as b goes to 0 from the left. The antiderivative of this is 3x to the 1/3. That goes from -8 to b, plus the limit as c goes to 0 from the right of 3x to the 1/3, evaluated from c to 27. Go ahead and put the bounds in there. The limit as b goes to 0 from the left. 3, the upper bound is b, so it's going to be 3b to the 1/3. Subtract the lower bound's -8. 3 times -8 to the 1/3. Plus the limit as c goes to 0 from the right of 3 times 27 to the 1/3. That's the upper bound. Minus the lower bound c, so it's going to become 3c to the 1/3. And it's just a process of evaluating these and then plugging in 0 where we see the limit. -8 to the 1/3 is just -2. -2 times a -3 is a +6. What's going to happen when we replace 0 in for b here? It's going to become 0. Plus the cube root of 27 is just 3. And the problem becomes 3 times 3, which is 9. Minus replacing 0 in for c in the second lower bound gives us 0. So the problem simply becomes 9 plus 6, which is 15. Number 4 from the handout, we see our bounds are both dealing with infinity, -infinity to infinity. This is a type 1 improper integral. And what we're going to do is we're going to break it into two limits. The first one's dealing with negative infinity, and the second one is dealing with infinity. And what's the place between negative infinity and infinity? That's going to be 0. First limit's going to look like the limit as a goes to negative infinity, integral from a to 0 of the function x to the 5th e to the negative x to the 6th dx, plus the other limit is going to include positive infinity as b goes to positive infinity, the integral from 0 to b x to the 5th e to the negative x to the 6th dx. And now it's just looking at these two limits of integrals and being able to integrate and then evaluate the bounds. What method could we use to solve this? It looks almost like integration by parts, but because we have an x to the 6th and an x to the 5th, it can actually be solved using a u substitution. Let u be negative x to the 6th, then du is negative 6x to the 5th dx. And since this negative 6 is an extra piece, we're going to go ahead and divide both sides by it. Du over negative 6 equals x to the 5th dx. The left side integral is going to be simplified. The limit as a goes to negative infinity, integral from a to 0. It's going to become negative 1/6, I'll put outside, e to the u du. The negative 1/6 came from rewriting du in this manner, and the integral is going to look like that, which is very nice to evaluate, plus the limit as b goes to infinity, the integral from 0 to b, also e to the u du. Now one thing I'm kind of not changing here, these bounds on both of them, they should are going to depend on u now, but since I'm going to go ahead and integrate, we'll see it's just going to be the same thing. So just kind of ignore the bounds for now. If we go ahead and integrate e to the u, the result is just e to the u. So this limit becomes, the limit as a goes to negative infinity, negative 1/6 e to the, now what's u? U was negative x to the 6th. After integrating, this is what we get. Evaluated from a to 0, plus the limit as b goes to infinity. And then this one will be the same thing. Negative 1/6 e to the negative x to the 6th, evaluated from, now the difference is it's going to be from 0 to b. Make this easier, let's factor out that negative 1/6. Plus the limit as b goes to infinity, e to the negative x to the 6th from 0 to b. All that has been done has been factoring out that negative 1/6. Okay, then it's just a matter of plugging in those bounds. Negative 1/6, we're going to get the limit as a goes to negative infinity of e to the 0 minus e to the negative a to the 6th, plus the limit b goes to infinity, e to the negative b to the 6th minus e to the 0. This negative 1/6 is multiplying the whole thing. And we'll go ahead and simplify and we'll get rid of those limits. E to the 0 is just 1. If we take negative infinity and we plug it into for a, now if we look at that very carefully, it's going to look like negative e to the negative infinity to the sixth negative of that. You take a negative number, raise it to an even power, it's going to become positive. Since it's going to become positive, this negative sign will make it negative, so it's really going to be negative e to the negative infinity, which is the same thing as negative 1 over a really big number, which is 0. So we can say that this will just become 0. Plus, using the same reasoning here, we're plugging in infinity. E to the infinity to the sixth, make that negative. It's still going to turn out to be 0. And then last but not least, negative e to the 0 is negative 1. And we get the following: 1 plus 0 plus 0 minus 1, which is really equal to 0. All that work for nothing. 0 would be the answer to this limit. Looking at number 5 here, it's the last problem from the handout. Because there's an infinity in one of the bounds, this is a type 1 improper integral. We're going to go ahead and evaluate it using a limit. The limit as b goes to infinity, replacing that upper limit of integration with a b, 5x e to the 2x dx. And to solve this integral, it's going to require integration by parts. Just have to choose our u and dv wisely so that the integral is simpler. So if we let u be, let's see, we have 5x and an e to the 2x. Let's let u be 5x. That means dv is e to the 2x dx. Go ahead and take the derivative of u. Du is 5 dx. Integral of dv is v, which is the integral of e to the 2x 1/2 e to the 2x. And we'll see very soon that this integral is going to be a lot nicer to work with. uv minus the integral of v du. U times v is right here, which is 5x, 5/2. If you multiply 5 times 1/2, that's 5/2 x e to the 2x minus the integral of v, which is 1/2 e to the 2x du, which is 5. I'll put the 5 above the 2. 5 dx right there. This is what should come out of the integration by parts. Don't forget the bounds. The bounds were 0 to b, and it's also a limit as b goes to infinity. 0 to b here, and then the other integral gets the bound 0 to b. Noticing that there's a 5/2 in common, go ahead and factor that out. 5/2 times the limit as b goes to infinity. And then go ahead and plug in the bounds. The first one becomes b e to the 2b minus, if you plug in 0, it's just going to turn out to be 0 for that lower bound. And put this all in brackets. Minus, I already took the 5/2 out in front. We got to integrate e to the 2x. The integral of e to the 2x is 1/2 e to the 2x evaluated from 0 to b. Hey, this looks familiar because we evaluated it over here almost at the beginning using integration by parts actually. So we got that one. It becomes 5/2. The limit as b goes to infinity. Right here we have The 0 just goes away. b e to the 2b minus 1/2 e to the 2b. And then our last term will be a 0. It'll cause this to be, let's see, minus 1/2 e to the 0. All in parentheses. So all I did there was evaluate the bounds from b to 0. Look what happens to this next step. We simplify it out. It becomes 5/2 times the limit as b goes to infinity, be to the 2b minus 1/2 e to the 2b plus 1/2 e to the 0 is just 1. Here's the problem. We're plugging in infinity. We're plugging in very large numbers for b. When we do that, we're going to get e to a very large number minus 1/2 e to a very large number. Well, it's like adding and subtracting infinity, but they're not necessarily the same infinity, so this whole thing is just going to turn out to be infinity. Because we do an integration problem, change it to a limit, and the result becomes infinity, the integral is called divergent. It has an infinite area under the curve. And we're done. Can't do anything else with that problem.